The Sun, our very own star, a giant ball of hot gas that has been puzzling scientists for centuries. It's no secret that the Sun is hot, but here's the catch. Its outer atmosphere, the corona, is hundreds of times hotter than its surface. Imagine a pot of boiling water where the steam is hotter than the water itself. This is the solar heating mystery, and it has left scientists scratching their heads, searching for an explanation. To understand this solar puzzle, we need to talk about magnetism. Magnetism is a fundamental force of nature, one that has fascinated scientists and laypeople alike for centuries. It's a force that can be both mysterious and incredibly powerful, influencing everything from the smallest particles to the largest celestial bodies. We all know magnets, those things that stick to your fridge. They come in all shapes and sizes, and they're a common household item. But have you ever stopped to think about how they work? What makes them stick to metal surfaces? The answer lies in the invisible force of magnetism. Magnetism is a force that attracts or repels certain materials, like iron. When you sprinkle iron filings around a magnet, you can actually see the magnetic field lines as the filings align themselves along these invisible lines of force. This simple experiment reveals the hidden structure of magnetic fields. But magnetism is more than just fridge magnets. It's a force that plays a crucial role in many aspects of our daily lives. For instance, the compass, an ancient navigational tool, relies on Earth's magnetic field to point north. Magnetic levitation, used in advanced transportation systems, allows trains to float above the tracks, reducing friction and enabling high speeds. It's all around us, even in space. The Earth itself is a giant magnet, with a magnetic field that extends far into space. This magnetic field protects us from harmful solar radiation and cosmic rays, acting as a shield that makes life on Earth possible. The Sun has a magnetic field too, a very powerful one. The Sun's magnetic field is generated by the movement of electrically charged particles within it. This magnetic field is responsible for many of the Sun's dynamic and sometimes violent behaviors, such as solar flares and coronal mass ejections. Think of it as invisible lines of force that flow around and through the Sun. These magnetic field lines are constantly shifting and changing, creating a complex and ever-evolving magnetic landscape. Scientists study these magnetic fields to understand the Sun's activity and its impact on the solar system. These lines can get twisted and tangled, storing enormous amounts of energy, like a rubber band stretched to its limit. When these twisted magnetic field lines snap, they release this stored energy in the form of solar flares or coronal mass ejections, which can have significant effects on space weather and even on Earth's technological systems. Let's get back to the Sun's atmosphere. The Sun, our closest star, is a fascinating and complex celestial body. Its atmosphere is divided into several layers, each with unique characteristics and temperatures. The surface of the Sun, called the photosphere, is about 10,000 degrees Fahrenheit. That's pretty hot. The photosphere is the layer we see with our naked eyes, and it's where sunspots, those dark patches, appear due to magnetic activity. But here's the strange part. The corona, the Sun's outer atmosphere, can reach millions of degrees. The corona is visible during a solar eclipse as a glowing halo around the Sun. Despite being farther from the Sun's core, it is significantly hotter than the photosphere. This is like heating a pot of water and finding the steam is hotter than the boiling water itself. How does this happen? It's a perplexing phenomenon that has puzzled scientists for decades. Heat doesn't usually travel from a cooler object to a hotter one. In most cases, heat flows from a hot object to a cooler one, following the second law of thermodynamics. It's like trying to boil water by putting ice cubes on top of it. It just doesn't make sense. So how does the Sun's corona defy this basic principle of physics? Scientists believe that the Sun's magnetic field plays a crucial role. The magnetic field lines twist and snap, releasing enormous amounts of energy that heat the corona. This process, known as magnetic reconnection, is a key area of research in solar physics. Observatories and space missions like the Solar and Heliospheric Observatory, SOHO, and the Parker Solar Probe are helping us understand these complex processes. By studying the Sun's magnetic activity, we hope to unravel the mystery of the corona's extreme temperatures. Understanding the Sun's behavior is not just an academic pursuit. Solar activity affects space weather, which can impact satellite communications, power grids, and even astronaut safety. So the more we learn about our star, the better we can prepare for its effects on our technology and daily lives. the sun remains a source of endless fascination and mystery. As we continue to explore its secrets, we gain a deeper appreciation for the incredible forces at work in our universe. Stay tuned for more discoveries about our amazing sun. Scientists believe that the sun's magnetic fields hold the key to this mystery. Imagine the sun's magnetic field lines as a network of pipes or channels. These pipes don't carry water, they transport energy. The energy comes from the sun's core, where nuclear reactions generate immense power. This energy travels along the magnetic field lines like cars zipping along a highway, up into the corona, heating it to those incredible temperatures. Section 5. Untangling energy with magnetic fields. But how exactly does this energy transfer happen? One theory suggests that the magnetic field lines, all tangled and twisted, can break and reconnect, releasing a burst of energy in the process. Imagine those rubber bands snapping. This sudden release of energy heats the corona, like a mini explosion going off in the sun's atmosphere. Section 6. A magnetic pathway to solar heat. The sun, our closest star, is a fascinating and complex celestial body. One of the most intriguing aspects of the sun is its corona, the outermost layer of its atmosphere, which is mysteriously hotter than its surface. Scientists have long been puzzled by this phenomenon and have proposed various theories to explain it. Another theory proposes that the magnetic field lines themselves vibrate and shake, like a guitar string being plucked. Imagine the sun's magnetic field lines as invisible strings stretched across its surface. When these strings are disturbed, they begin to vibrate, creating waves of energy. These vibrations, called waves, travel along the magnetic field lines, carrying energy from the sun's interior to the corona. These waves are known as Alfvén waves, named after the Swedish physicist Hannes Alfvén, who first proposed their existence. Alfvén waves are a type of magnetohydrodynamic wave, which means they are waves that travel through a plasma, a state of matter found in the sun. Think of it as a wave traveling through a rope. When you shake one end of the rope, a wave travels along its length, carrying energy from one end to the other. This is similar to how Alfvén waves travel along the sun's magnetic field lines. You shake one end of the rope, and the wave carries energy to the other end, even though the rope itself doesn't move much. This analogy helps us understand how energy can be transferred through the sun's magnetic field lines without the field lines themselves moving significantly. Similarly, magnetic waves could be transporting energy from the sun's interior to the corona, heating it up. This process is crucial for understanding the dynamics of the sun and its impact on the solar system. The energy carried by these waves can heat the corona to temperatures millions of degrees hotter than the sun's surface, a phenomenon that continues to intrigue and challenge scientists. By studying these magnetic waves, we can gain deeper insights into the behavior of the sun and its influence on space weather, which can affect satellite communications, power grids, and even climate on Earth. Section 7. Nanoflares, tiny explosions, big impact. Scientists have also discovered tiny explosions called nanoflares happening all the time on the sun's surface. These nanoflares are much smaller than solar flares, but they release a tremendous amount of energy. Imagine billions of tiny firecrackers going off at once. That's a lot of energy. Some scientists believe that these nanoflares, powered by the sun's magnetic field, could be a major contributor to coronal heating. Section 8. Waves of energy, riding the magnetic highway. So, we have these constantly breaking and reconnecting magnetic field lines, vibrating waves traveling along them, and countless nanoflares erupting. It's like a cosmic dance of energy, all orchestrated by the sun's powerful magnetic field. This energy, carried by the magnetic fields, heats the corona to those baffling temperatures, solving the mystery of the sun's super-hot atmosphere. Section 9. A new perspective on the sun's furnace. Understanding how magnetic fields heat the corona isn't just about solving a cosmic puzzle. It has significant implications for our understanding of how stars work in general. The sun is our closest star, and by studying it, we learn about the processes that power other stars in the universe. Section 10. Unlocking the secrets of our star. Moreover, the sun's magnetic field has a direct impact on Earth. Solar flares and coronal mass ejections, those massive bursts of energy and particles from the sun, can disrupt satellites, communication systems, and even power grids on Earth. By understanding how magnetic fields work on the sun, we can better predict and prepare for these space weather events, safeguarding our technology and way of life. Section 11. Future Explorations, Illuminating the Sun's Mysteries. The sun, with its intriguing magnetic dance, continues to fascinate and challenge our understanding of the universe. New missions and telescopes are being developed to study the sun in even greater detail, unraveling the complexities of its magnetic field and its role in heating the corona. As we delve deeper into the heart of our star, we're bound to uncover even more surprises, illuminating not just the secrets of the sun, but also the fundamental workings of the cosmos.